There are many functions that take in the context as one of their arguments. The context can be thought of as all the information describing the current state of a part studio. Functions like primitives and operations enact change on the context, while queries and evaluations retrieve information for use in other functions inside the code. Many of these functions take in geometric data as some of their arguments. In this video, we will focus on the most common geometric custom object types and where you might use them. Here is a list of the geometric objects frequently used to define functions that operate within the context of the part studio. Vectors are arrays with 2 or 3 entries depending if they are 2 or 3-dimensional. Lines are maps that contain an origin and direction, defined by vectors. Planes are maps that contain an origin, normal direction, and optionally an x direction defined by vectors. Coordinate systems are maps that contain an origin, x-axis, and z-axis, defined by vectors. Value with units contains a value with a unit. We already discussed value with units in a previous video, but let's take a deeper look at each of the other object types. Vectors are the foundation for many geometric types and are used explicitly in many functions that interact with the context. Vectors are used either to define points in space or direction. For points in space, vector components need length units, but for direction, they are unitless and normalized. There are a lot of functions in the standard library that manipulate vectors, such as normalizing or getting the dot or cross product. Lines are a helpful type for many geometric functions, but are also used explicitly as the axis when creating a revolve feature in the context. Planes are used in functions throughout the standard library. They are extremely important for sketching, but are also used in many other functions. Coordinate systems are also used throughout the standard library. Coordinate systems are required to create several other custom types such as circle, ellipse, cylinder, and cone. They are also needed to create mate connectors. Coordinate systems are very similar to planes and can easily be converted using the plane function. Conversely, planes can also convert to coordinate systems using the coord system function. The debug function is a simple example of how we can cross over to the context. It prints information about the argument to the FeatureScript notices and, if possible, highlights the entity in the model space while the feature dialog is open. Inside a new document, add a new feature studio and feature. Name them spheres. Define a vector with the value 111 inches. Add a debug function with the vector as its second input. Now, a point shows in the model space at the correct position while the feature dialog is active. Define a new constant for a line. A line takes in one vector to define its origin and another vector for its direction. Use the previous vector as the origin and add another vector with 2 entered for the x, y, and z coordinates. When a vector is used for direction, units are not necessary. Create another debug to display the line. The result is an arrow starting at the previous point, going in the direction of the second vector. The debug function only creates temporary visual feedback when the feature dialog is open. It is best for troubleshooting. If we want to enact a permanent change to the model, we need to use a function that creates or changes bodies in the context. Primitives are basic 3-dimensional shapes. We already used the f-cuboid primitive in previous videos. Sketch functions build sketch geometry. Many of them have the prefix sk in the name. We will cover sketching in depth in another video. Operations are the primary way in which changes are made to the context. All operations have the prefix op in the name. Onshape features are the FeatureScript functions used for all of the standard features. These are not best suited for programmatic use because they combine many operation functions together. For example, the extrude feature combines the op_extrude, op_boolean, and op_draft features, resulting in 29 parameters. Comment out the debug actions and define an op point. It requires the context, unique ID, and a point to define the location. Use the default values for the point. When you run the feature, a selectable point is created that you could use for future features. Note that the point feature is contained within the custom feature, so it does not appear as a separate feature in the feature list. A unique ID is required for all operations in Onshape. New operations default to ID plus operation name. The plus operator is not the same as string concatenation, which is a tilde. The ID is not just one ID string, but an array of IDs that create a folder-like structure. This hierarchy is extremely important in for and while loops. Create a for loop that goes through 2 iterations using I as the counter. Put the op point inside the for loop. Multiply the vector for the point by I. Commit the code and run the feature. There is an error in the FeatureScript Notices panel that indicates there is a duplicate ID. This is because the ID of the point needs to be unique for both iterations. Remove the 1 from point 1 and put an I at the end of the ID. Because there is only one feature in the loop, it successfully creates the points. However, this is not a good way to iterate the ID because it causes an error if other features are added. Create an op sphere within the for loop after the point. Correct the ID to use I. Leave the default value for the radius, but use the location of the point for the center. This places the sphere around the point. In the Part Studio, there is the error that the point ID is used at 2 non-contiguous points. Each parent ID must be contiguous and cannot be revisited once another parent ID has started. In this case, the parent ID switches from point to sphere, but when the loop moves to the second iteration, it tries to go back to the point ID. There are better ways to define the ID to avoid this error. To correct this, move I before the point and sphere IDs. In the Part Studio, the error is gone and the feature executes correctly. Changing the order of the ID ensures that the counter is the parent ID, removing the opportunity for it to repeat. You could take it a step further and add a static identifier before the counter in the ID to make it easier to reference in a query. Queries are used in FeatureScript to reference topological entities such as bodies, faces, edges, and vertices. A query can reference 0, 1, or many entities. Information from queries can be used in FeatureScript as arguments for operation and evaluation functions. Many queries can take in another subquery as one of its arguments. Queries are functions that have the prefix q, such as QEverything, QEdgeAdjacent, and QCreatedBy. The evaluate query function turns a single query into an array of queries that return exactly one entity each. You do not need to use this function for standard library functions because they take in the query directly as an argument. Evaluate query is useful to iterate through a query. You could use it to process each entity differently depending on its type. You can also use it to count the number of entities returned. To quickly test a query, the debug tool is very effective. Open the Spheres custom feature from the last video. Create a new debug function. Add QEverything to the second argument. QEverything is the broadest possible query. It returns all entities within the model space. Go into the feature dialog in the Part Studio, and everything is highlighted red, including the standard planes and origin. The FeatureScript Notices panel indicates how many entities of each kind the query resolves to. Another common query is queue_created_by. Instead of querying everything, it allows you to pass in the ID of a feature. Change queueEverything to queue_created_by. Add ID plus sphere loop plus 1 plus sphere to the argument. It captures the sphere from the first iteration of the for loop. If you want to capture the point as well, remove sphere from the ID. Now everything created by the first iteration is highlighted. Furthermore, if you want to select everything created by all iterations of the loop, remove everything after sphere loop. This is why adding the string in addition to the counter is helpful when defining IDs for looped portions of code. Some queries act as a filter to further narrow the results of a subquery. For example, queueContainsPoint returns anything that satisfies the internal query and touches a certain point. Surround queueCreated_by with queueContainsPoint. The first argument is the original query. The second argument needs to be a point, defined by a vector. Use a vector at position 0, 0, 2. This intersects the outer surface of the second sphere. It highlights only the second sphere because it is the only one that contains that point. It is also valid to use chaining syntax, which avoids nesting and makes it much easier to read. It starts with the base query, and as you go to the right, you can apply more filters to refine the results. For this example, this query would start with queueCreated_by, followed with queueContainsPoint. Each query is separated with a chaining operator that looks like an arrow. You can use body type and entity type to filter queries further. Body types include solid, sheet, wire, point, make connector, and composite. Sheets are surfaces that are not a part of a solid body. Wires are curves existing outside of surfaces or solid bodies. Points are independent points such as the origin or the two-op points we made in a previous video. Each body includes one or more entities. Entities are vertices, edges, faces, and even the bodies themselves. For example, a cube is a solid body type, and it is made up of entities that include one body, 12 edges, 6 faces, and 8 vertices. Entity type is an optional argument for many queries, or can be used in a queueEntityType filter. It is important to note that edges are not just the intersection of two faces, and vertices are not just the points on a solid. For example, a wire body contains edges for the segments and vertices on its endpoints even though it is not a solid body. Similarly, a point body has a single vertex entity. In the Feature Studio, the current debug query resolves to one solid body and a face. Add the optional argument EntityType.body to the queueCreated_by subquery. It only returns the body. Change the point filter to the center point of the second sphere. It returns the two spheres and the point at the center of the second sphere. Add another filter for only solid bodies. It returns only the sphere bodies. Change the body type to point. Now it returns the point body. Evaluation functions are essentially the opposite of what an operation does. An operation takes the values within FeatureScript and uses them to modify the context. Evaluation functions take entities in the context and return values like vectors and planes that can be used in FeatureScript computation. Create a constant named myQuery and set it equal to the query that was inside the debug feature. In the Spheres custom feature, create a constant named myQuery and set it equal to the query that was inside the debug function. This query selects the center point of the second sphere. Create a new constant named position. Set it equal to the result of a EV_vertex_point function. This evaluation takes in the context and a vertex entity as its arguments. Set the vertex to myQuery. Add a debug function to display the point. Remove or comment out any other remaining debug functions for clarity. This script now goes full circle. We started with a vector, created 2 points that related to it, queried the second point to select the vertex, and then translated the point back into a vector value that we can use for further computation. Another common evaluation function is the EVBox3D. It returns a box3D custom type. A box 3D is a map with 2 vectors that define the opposite corners of a bounding box. Create a new constant named spherebox3D and set it equal to the EVBox3D function. The topology parameter is a query that finds entities to define a bounding box. Set the topology to QEverything and debug it. The box 3D shows as a map with 2 corners defined by vectors in the FeatureScript Notices panel. In the model view, the box encompasses not only the 2 spheres, but also the outer bounds of each of the primary planes. We only want it to surround the spheres. Add QBody type to filter only solid bodies. Now, it only bounds the 2 spheres. Let's take a look at another example. Copy the evaluation document in the key takeaways for this video. This custom feature already has a query parameter. It allows the user to select an edge, face, or vertex and stores it in definition.userSelection. The user's selection results in a query, so we need to use evaluation functions to translate it into geometric FeatureScript values. First, the code needs to discern the difference between a face, edge, or vertex so that it can call the appropriate evaluation. The best way is to filter the user's selection for specific entities to see if the resulting query contains anything. Create a new if statement and use isQueryEmpty for the condition. The isQueryEmpty function checks to see if there is anything in the result of a query. It returns a true or false result. Enter QEntityFilter to filter the user's selection for faces. Add the not operator because if it is not empty, we want a true result. Add a printLine function to notify that you have selected a face. Repeat this process for the edge and vertex result. Create a basic rectangle extrude in a new Part Studio and make sure the appropriate type prints in the FeatureScript Notices panel for each selection. Now we need to add evaluations to turn each selection into the appropriate geometric object. Evaluate the face into a plane. Create a constant named selectedFace and set it equal to the result of an EVPlane function. Enter user selection for the face. In the Part Studio, the plane is created at the center of each face. Optionally, you can use EV surface definition. EV surface definition is more flexible because it automatically determines whether the face is a cone, cylinder, plane, sphere, torus, B-spline surface, or other type, and returns the appropriate object or unspecified map for the face. Replace the EV plane function with the EV surface definition function. It automatically determines it is a plane and returns the correct object. Use the EV edge tangent line function to evaluate an edge to a line. It may seem strange to use a function for tangency, but for a straight line, the result is coincident. It requires an edge for direction and a number in the range of 0 to 1 to choose the origin of the line. Create a constant named selected edge and set it equal to the result of an EV tangent line function. Set the edge to user selection and parameter to 0. Add a debug function to see the result. In the Part Studio, the line starts at one of the endpoints. The FeatureScript Notices panel prints the map for a line. Finally, add a constant for the vertex. Use the function EVVertexPoint. Set the vertex to the user selection. Add a debug to see the result. The FeatureScript Notices shows a vector for the location of the vertex. It is important to understand how to identify and fix issues in the code. Without knowledge on debugging, it may be difficult or impossible to diagnose why features are failing or generating unwanted results. We already utilize the debug and print line functions to gain insight into a feature, but there are a few more tools to explore. Open the spheres document from previous videos. The FeatureScript Notices panel shows all printed outputs as well as runtime and thrown exceptions. In the Spheres custom feature, remove or comment out any remaining print line and debug functions. Change V to just an array. This causes an error in the code. Each error or warning shows line numbers associated with problematic function calls, including imported documents such as the standard library. Selecting the warning takes you directly to the line that has an issue. The line function fails because V is now an array instead of a vector. A vector with units is required to define the line's origin. Type check issues are not noticed during regular execution for performance reasons, but monitoring does more thorough checks. Turn on monitoring for the Part Studio in the pull-down in the top right. The line with the type check issue highlights in the Feature Studio. Additionally, with monitoring on, committed changes are automatically executed without having to return to the Part Studio. We have already used monitoring for this reason in other videos. Change V back to a vector. Once committed, the error is removed from the FeatureScript Notices. While testing the functionality of a Feature Studio, we recommend opening the affected Part Studio in a separate window, then splitting your screen or using a second monitor to get instant visual feedback on what changes to the code result in. This technique won't be utilized in many of our videos due to visibility constraints.